Alright, first of all, this is the lab. Okay, for the exercise 1, here we need to create and test the function that given Euler axis angle information returns the rotation matrix. So here we define the axis 100 and we put an angle of 45 degrees but in radians. Alright, we define the rotation matrix using this function here. We make this axis angle and we transform to a matrix. If we go to the definition, here it is, and here we do this and we use the formula of Rodriguez with the cosinus and sinus and the tan. Alright, and here we get the matrix with Rodriguez formula. Alright, then we print it here to see the result in the book mode. Then we calculate the determinant that we have done this function with recursivity here with the initial case, which is the size 1 and the size 2. So here we made it by iterating with this matrix and with recursivity. Alright, we get the size of the vector of the rows and then of the columns and the rows, and we keep it, we push it, and then we do this. If it's odd, it's minus. If it's even, it's not minus. And here we multiplicate that to the determinant, because if it was a 3 by 3, we would be this case here, and then we will recursivity until we end the matrix, so it would be called all the time. Okay, that's the determinant. It's really easy. Alright, and then we print it, the determinant, and then we transpose the matrix, which is really easy because it's to put the j in the I and the I in the j of the rows and the columns. It's like this, really easy. Then we do a function to see if the transpose is the inverse, and here it is. We make a tolerance because in the last lab we didn't do it and we have a lot of mistakes, so here we make it, and here it is the tolerance. We do it like this, and with the tolerance and all of that we get the result, and we see if the transpose is equal to the inverse and do it like that. Alright, then we print it, this inverse, and we put it in the debug mode if it's inverse or if it's not. If we go to the debug mode, we could see this matrix, what is the rotation, the determinant which is 1, and we transpose the transpose is equal to the inverse, so we do it right, it's well implemented. Alright, then exercise 2, we create a function that implements the quaternion multiplication. Alright, and then create a function that given a vector and a quaternion return the vector rotated by the attitude encoded in quaternion using quaternion multiplications. Alright, so here we define the Euler angles, which is 0 0, and with this, that is the 180 degrees, we convert these Euler angles to quaternion with this function here using this formula, and then when we get it, we have the quaternion, and the vector is like this. So for example is 1 0 0, and we rotate it with quaternion, this vector, and we get the vector rotated by the quaternion, which is here. Go to definition, and it's like here, and here is when we use the multiply quaternions, which is really to see to do the formula, because it's a 4 by 4, so it's a multiplication simple, so it's like this. we return this value and all of that. Alright, and we multiply here and we see that the result is this size and this multiplication. Alright, and here we will return this quaternion, this vector, sorry. Alright, and then we print it and we see if it's the same as we expected, which would be 0, 1, 0. So we go to the debug mode, and here it says the rotated vector is 0, 1, 0, and the expected is 0, 1, 0. So it's well implemented and it's right. Alright, then exercise 3. In exercise 3 we have made it to, because we didn't know how to plot all this, and with a friend which is doing engineering of telecos, talk about the matplot and talk about us, and they explain us to do it with Python and how to plot it. We have a little help for doing that. But first of all, we created a document text to save all the data of the 100 matrices of the angles, the Euler angles axis. And doing this, we save it. Well, here it is, the random values. Alright, we normalize the axis. Alright, and we create the rotation matrix, which is the same function that we have used before. And then we trace it. That the trace it only what does is to save the information and do it in once. It's like that. It's not nothing more. It's to trace the information of the matrix, and we write it in the text, and here it is. And then we close, obviously. And then if we go to the debug mode, it says that rotation matrix and the trace is saved to the rotation trace data.text. So we go to this, that is here, rotation matrix, rotation trace data here, and here are all the randoms, and here it is. Alright, so if we do the command that explained us, and to plot we have used this document, we import it, we load it, and then we open it and save that to plot it. So it was explained with a friend and we understood that. We didn't know how to do it, but now we know. Then we go to the debug mode, and here it is. I have to go to the terminal to make this. So view terminal, and we put this command to this document that is called, we call like that, plot trace, like here. And here it is, and it's like we expected, a sinusoidal form of this. So as we expected, here is the same like here, and this represents that it is rotating, and it doesn't change nothing, it's only that it's rotating. And that's it, because this value is the same that this value and all of that. Here the radians angles 0, 0 to 17.5, and the trace of the rotation matrix. Alright, and here would be the exercise 3. Alright, then the exercise 4, we created a function that given a set of Euler angles return its respective rotation matrix. Alright, here we define the Euler angles, which is like that, 45 degrees, and here 30 and all of that. Alright, we convert these angles to rotation matrix with the function, with this function that we have used before. No, before we have used it, okay. And we do it here, and with the three values here, and the cosinus and the sinus, we get these values that using this formula we get the matrix. Alright, when that is done, we print it to see the result, and then we convert it to Euler angles another time to see if the value is like we expected. And if we go to the book model, well, wait a moment, we can predict the angles, yeah, and if we go to the book model, it's like this. It's expected rotation matrix here, here, and all of that. And if we see original angles 0.780 and here 0.82. Here we have done a tolerance because the result it's not the same, but we do it by a tolerance to see if it's really parecido. It's like this, and here is 1.0, 1.0, 0.5. That's, but with this tolerance we made it, it says that it's right, but it's like this, and that would be this exercise. We compare the vectors, and here we make it by this tolerance, by the tolerance that is in this function, that is here, this tolerance. All right, and then we, in the exercise 5, we need to do these functions of that that we have here, that here is return the Euler rotation given a rotation matrix. So here we have the Euler to matrix that is doing the formula. Then the same with matrix to Euler with the formula that we have seen in the PowerPoints of maths, with the sin and tan and arctangent and something and all of that. With this formula we get it. Then Euler to quaternion, which is here, returns the quaternion here, and here we return the quaternion of 4/4, which is this one, and with the formula of cosinus and sinus of this, and we get the quaternion. And then the quaternion to Euler, we do the formula to get the same of a Euler angle. We get the axis. Alright, then Euler to rotation vector, we get the rotation vector by doing the Euler to matrix, which is this function we have to it before. We do the matrix to Euler 2 to get the axis that we have seen before, and then the rotation vector is like the multiplication of this, and we get the vector. So it's like that, and then the same, but in the inverse, we get the squared root of that, and we have the angle, and then with the angle we get the axis dividing by him. All right, and here will be the exercise 5. The exercise 6, we have a lot of mistakes. We have corrupted something, and I don't know why it's like that. We have tried, but we haven't reached a conclusion and nothing like that. I think it was because we have used null pointers and all of that to make this function that have a lot of components and it returns something that could be one thing, could be a vector or an array or a matrix, and like that. And we have a lot of mistakes, and we haven't done it because we haven't reached any solution of that. It was really complicated for us to do, so we haven't done. And that's it. That would be our lab and our things. So thank you.